Hello students, this is Katie. I'm here, I'm going to do a run through of all of the practice problems from the 2018 midterm and the 2019 mini term 3 to help you all prepare for the midterm that's coming up on the 18th, this upcoming Wednesday. I'm hoping that this will just give you guys another resource to prepare now that the class is online. Before I jump into everything, a quick disclaimer. I am using a new piece of software for me, and so hopefully that there aren't any major bugs. And additionally, I'm recording my voice on the microphone that came with my headphones, so hopefully you can hear me pretty well. Next, before I start jumping into the problems, I do want to let you guys know that because this exam is going to be an at-home exam as well as an open note, open book test, I don't know if how similar the format's going to be, how similar the difficulty is going to be. It is almost certainly going to be more difficult because you do have access to your entire textbook while taking the exam. But in general, I would still use these as a good guide for how Dr. Nigra writes these problems and a good place to start on studying. And I'm still planning on holding office hours on Tuesday. Dr. Nigra and Gabe are as well, so make sure you guys are coming to office hours. Hopefully, if I can edit this correctly, somewhere on the screen right about now, I will pop up with the time code for when I start each problem. If you see that, I was successful. If you don't see that, I was not, and you're just going to have to scroll through. I apologize for that if I failed. So, getting started, I'm starting on midterm 2 from 2018. If you can see up here, I've marked which questions are more suited to mini-term 3 and which problems are more suited to mini-term 4. Hopefully this will sort of give you an idea of what you should be studying from this particular exam. I will only be going through problems that are appropriate for mini-term 3. I'll save mini-term 4 for when we get there. So scrolling down, our first problem is going to be problem 2. It's the 2 reactors in isothermal contact. Now, before we get into this, I want to highlight a couple of things from the problem statement. So it says a new engineer has 2 CSTRs which are placed in perfect thermal contact with each other, and they have no other heat transfer to the surroundings. What this means is that there is no heat exchanger on this system, and when I look at the entire boundary of the system, this thing I'm, marking out right here for you, there's no heat or energy leaving that boundary that I just drew. This will be important in a few minutes. Next, we have some information about CSTR1, which is the CSTR here inside. It's an elementary phase reaction. A goes to B at T equals 500. And there's some more information for you guys to read. We have some information about what enters the CSTR and etc. In CSTR2, which is this outer one, and this is kind of confusing. This is volume 2, just to be clear. We have reaction C goes to D, and temperature is 500, the temperature of the reaction. And then we have more information. We know pure C enters CSTR2 with a concentration and an inlet flow rate. Oh, I should also note that CSTR1 is isothermal. That's also important. So let's get started working through this problem. So for part A, what is the conversion X1 in CSTR1? Now, like I noted before, CSTR1 is isothermal. So in this case, it's just a design equation problem. Now, of course, the design equation for a CSTR is volume equals flow rate A X1 over negative RA. negative Ra in this elementary phase reaction is going to be equal to K Ca. So now we have Fa naught x1 over K Ca. Nope, that's fine. And of course we can replace Ca with Ca naught 1 minus x1. Now we know we can replace Fa naught is Ca naught volumetric flow rate, and then we end up with volume is equal to Ca naught volumetric flow rate x1 over K Ca naught 1 minus x1. Now since we are given the residence time, tau, we're going to want to plug in for that. So tau is going to be equal to volume divided by volumetric flow rate, and doing some fun little arranging, we get tau K is equal to x1 over 1 minus x1. Now, we need to solve for x1. I am going to make some assumptions that you guys can do some algebra. So if we come up here and we pull out tau and K, we can say that 2 minutes times 0.5 inverse minutes is going to be equal to x1 over 1 minus x1. And when you do the algebra, you get x1 is equal to 0.5. Part B. If CSTR2 is operated isothermally, or the reaction temperature T1 is equal to the inlet temperature T0 of 2, what is the inlet molar flow rate of C that is required to hold both of the reactions at T1? So we are looking for FC0. So to do this, we're going to start by doing what we do every time we do non-isothermal systems, or systems where all of the heat isn't anyway. So let's start with our mole balance, which is, of course, our design equation. So from that, we have volume is going to be equal to FC0 x2 over negative R2, which is going to be equal to, using the same assumptions I used before, I can plug in so from here we can plug in our rate. We've got FC0 x2 is equal to K C0 1 minus x2. Before we move on from here, let's look at our energy balance. Now, from our basic energy balance, if we are in an isothermal system, our basic energy balance becomes dE dt is equal to Q dot minus FA naught X delta HR. This specific equation has two assumptions. One, it's isothermal, so T is equal to T naught. And two, that T is equal to Tref, or the heat of reaction that you are given is equal to the reaction temperature. Your reference has to be equal. Yeah. So, of course, we are at steady state, so this goes to 0. But in this case, we need to be looking at our entire system. So we have to be looking at both reactions for this entire system to be at steady state. So instead of using this, we're going to say that Q is going to be equal to FA naught X1 delta HR of T1 plus FC naught X2 delta HR T of 2. And of course, we defined earlier that if we are looking at this entire system, it is adiabatic, so Q will be 0. So now we need to, well, now we have all of the equations that we need to do it. So we are looking for FC naught, and we have, at this point, we kind of have two equations, two unknowns, because we know everything except for, let me grab a different color for this, X2 and FC naught. So you can kind of solve this any way you want, but I think the most simple way is to plug in to our energy balance, solve for X2, and then solve for FC naught from there. So that's what I'm going to do. This is also helpfully what the solutions show, so that is useful. So from our mass balance, I can get that FC naught X2 is going to be equal to oh my gosh, words. It should be equal to V K C C naught 1 minus X2. This will be important in a second because if you can see that this is the easiest way to plug in here. So I can now write this as FA naught X1 delta HR T1 is equal to negative V K C C naught 1 minus X2 delta HR T2. From here, it's just solving for X2. Take all of the numbers from before, plug in. I'm not going to write it here because I'm assuming that you guys can do this, and you get X2 is equal to 0.8. And now I can plug in to my design equation and solve for FC naught, in which case I get FC naught is going to be equal to V K C C naught 1 minus X2 divided by X2, and you get a value of 125 moles per minute. On to part C. This is probably I don't know if it's the hardest one, but it might be the hardest because you do have to make a judgment call qualitatively at the end. So for this one, we are finding an expression for, here, let me highlight it, an algebraic expression using a bunch of symbols for FC naught that is required to maintain both reactions at T1 qualitatively, and then we have to qualitatively say how this compares to what we found in B, so when reactor 2 is also isothermal. So in this case, what changes is our energy balance. So last time I wrote the energy balance down for when we are in an isothermal system. Now, the full energy balance, and you can find this in class 11 slides, dE dt is equal to Q minus WS minus FA naught, CPI theta I, T minus T naught minus FA naught, XA delta HR of T. This, of course, is under the assumption that T is equal to TR. So I removed the expression for delta C hat that's in this full expression if you look at the class 11 slides. Now, getting rid of things, that 0 that's 0. And if, of course, we look at the entire system, both reactors, that is 0. For reactor 1, that's 0 for reaction 1. So let's go over everything that we have here. So now we have 0 is going to be equal to delta HR1 FA naught X1. That is this term for the first reactor. For the second reactor, we have plus delta HR2 FC naught X2 plus, let's actually label these F primes so that we know it's a different problem. Also because that's the nomenclature given in the problem. Plus T1 minus TO2 CP FC naught prime. Okay, cool. From here, all we have to do is solve for FC naught. So if we do that, we get negative HR FA naught X1 equals FC naught prime times the quantity delta HR2 X2 plus T1 minus T naught 2 CP. So FC naught prime is equal to this. I totally started copying the top instead of the actual value. Sorry about that. This. Now, that's our final expression. That's the answer to this. Now let's talk about the qualitative question here. So this right here. Now, in part B, we would have gotten an expression, and if you had solved everything, you would have gotten an expression that looked like this. FC naught is equal to should have gotten that because, of course, that would have been 0. If we're talking about which one of these is bigger, or how are they different, our answer FC naught prime is going to be smaller than FC naught. So this should be true. FC naught prime is less than FC naught. Because if you can see, the denominator of this is going to be bigger. Just the denominator itself is going to be bigger than that. So this value must be smaller, this one. It has to be smaller because the denominator is bigger. And that's it for that problem. So problem 3, we're skipping. There are some parts of problem 3 that are applicable to this exam, the selectivity stuff specifically, but we will talk about selectivity on a problem from the Miniterm from 2019, so I'm not going to discuss it here because this also has mass transfer limitations, which we have not gotten to yet. So we're going to skip it and come straight to problem 4. Problem 4 is a multiple steady state problem. In general, I think these are fairly straightforward, especially graphs of generation and removal that you see here. So if we look at this picture, R of T is the heat, heat removed, and G of T is the heat generated. So for part A, we are marking the steady states on the graph, and We're going to number them. So in multiple steady states or in non-isothermal reactors in general, we are looking for where the heat removed and the heat generated are equal to each other. So anytime these two lines intersect is a steady state. So we'll label them 1, 2, 3, and 4. Now, for part B, we are classifying each steady state as stable or unstable. Mark the stable with an S and the unstable with a U, and then we justify. Now, how to identify if it is stable or unstable? For doing that, at each one of these points, so let's look at point 1, what we do is we're going to look at a point just slightly increased in temperature, so just slightly more along this axis. And in stable points, so if it's stable, at T just slightly greater than your point, you will see the heat removed will be greater than the heat generated. Now, why is this true? This is true because if heat generated is bigger than heat removed, your reactor will continue to increase in temperature because there is more heat in there and the heat needs to contribute to something. That energy will contribute to something. If the reactor continues to increase in temperature, it will just move until you reach a different steady state that is stable. Hopefully that made sense to you all. Of course, unsteady state or unstable, if you couldn't figure this out, G of T will be greater than R of T. By this rule, point 1 will be, if we go a little bit over, we can see that R of T is greater than G of T, so this is stable. Actually, let me write this in a different color so that you guys can see it a little bit clearer. Let's throw this in blue. So this is going to be stable. 2, increase a little bit, generated is going to be bigger than removed, so this is unstable. Like I was saying before, if I increase in temperature a little bit, you can see it's going to continue increasing in temperature until it reaches this point. Point 3, increase a little bit, it's just going to, the heat removed is going to just knock it right back to this point, so it is stable, and 4 is unstable. Now, for part C, it's asking, would the number of steady states increase or decrease as the reactor becomes more isothermal? How can one make a non-isothermal reactor more isothermal? So let's talk about what changes on this graph. So okay, so as the reactor becomes more non-isothermal, your line, so you have this, and then you have that's your generated line, so your removed line. Bear with my drawing skills. As you become more isothermal, this will move more and more vertical until your vertical line is your isothermal line. As you can see, as my line moves, changes its slope so it's more vertical, the number of steady states decreases. Now, how can one make a reactor more isothermal? Really simple. You can add a heat exchanger. Now, of course, this is because a heat exchanger will allow you to increase the amount of heat that's being removed, and that can affect the slope of that line. Oh, that is the last problem from this midterm that is applicable to this mini term. So let's hop over to the next one. So let me scroll up to the top. This is the Miniterm 3 from 2019. Sorry, I have to find my notes. So this is going to be, as far as I know, fairly representative of what you should expect. Problem 1 is a reactor design. We have an irreversible liquid phase reaction taking place in a jacketed and well-mixed batch reactor. The reactor has constant volume V, and it is second order in A, with that being our rate law. We have a temperature and a rate constant. It's exothermic. We know a whole bunch of other stuff. Now, part A, write an expression for the reaction time T as a function of known values and conversion of A and XA. Assume that the reactor is operated isothermally at temperature T. Show your work. This is a mole balance problem. It's just a design equation problem. Of course, our basic... Oh, wrong pen. Sorry, everybody. Of course, our mass balance, just a general mole balance, it's going to be negative RAV is equal to DNA dt, which is going to be equal to dCAV dt, which is equal to... I'll stop talking while I'm writing this. One sec. This term, product rule, this should look very familiar. That, of course, is 0. So now we end up doing some simplification. We end up with dCA dt is equal to negative RA, which is equal to this, which was given in the problem. Solve here. It's just basic algebra, so I'm going to separate and integrate. So I have dCA CA squared that I'm going to be integrating from CA naught to CA is going to be equal to K integral from 0 to T of dt. This, of course, is 1 over CA naught minus 1 over CA equal to KT. I dropped a negative sign. This should be positive. This should be negative. Excuse my bad math. Now from here, let's plug in CA is equal to CA naught 1 minus XA. So we end up with 1 over CA naught minus 1 over CA naught 1 minus XA is equal to negative KT. Now, doing some fancy algebra math, you end up with T is equal to 1 over K CA naught times the quantity 1 over 1 minus XA minus 1. I know I skipped some algebra steps. I'm really assuming that you guys can get there. And helpfully, just like what happens fairly often, Dr. Nigra gave you the answer here in case you couldn't get there. So the math on the rest of it would be the same. So for part B, when the reactor is operated isothermally at temperature T, what is the time needed to reach 90% conversion? So T is equal to 1 over K CA naught. This is from the last part. We end up with, by plugging in XA is equal to 0.9, I end up with 1 CA naught times 0.1 minus 1. And this gives you T is equal to 9 over K CA naught. All right, next we are going to answer part C. In this part, we are looking for the percentage of the total heat that will be transferred in the first quarter of the time needed to reach 90% conversion if we are at isothermal conditions. Now, if we're under isothermal conditions based on our heat balance, the heat produced Q will be equal to delta HR X FA naught, or in this case, X NA naught, because we're in a batch reactor. So, based on this, the percentage of the heat transferred will be equal to the percent conversion. They're proportional, so these percentages should be the same. So, to solve this, we just need to figure out at what the conversion is at 1/4 of the time. So we know that T is equal to 9 K Ca naught. So in this problem, we will be looking at 9/4 K Ca naught. So plugging this into our equation from part A, we've got 9/4 K Ca naught should be equal to 1/K Ca naught, 1 minus 1 minus X minus 1. Those cancel. Moving the 1 over, we end up with 13/4 equals 1/1 minus X. And do some algebra, and you get that X is equal to 69%. So 69% of the heat is transferred in the first quarter of the first quarter. Cool. Continue to scroll down. So, assuming that the reactors is still operated isothermally at temperature T, cooling water is available at a constant temperature T cool. You are given the overall heat transfer coefficient U, as well as other values that are given, and we need to find A. So, if you can remember from heat transfer, and I think this is talked about on like the notes from like class 14 or 13, Q of a heat exchanger is going to be equal to UA, the temperature of our reactor, minus T cool. And of course, Q of our heat exchanger, the heat going into our heat exchanger has to be equal to the heat being generated of our reaction, which, as I said before, is equal to delta HR X FA naught. So, from here, I can say that UA T minus T cool is going to be equal to delta HR X FA naught. Of course, that's fine. Actually, it shouldn't be FA naught because we are in a batch reactor, so NA naught. We know this term right here is also equal to VRA. Through our mass balance. Sorry, I'm mincing words here a little bit. So plugging that in and plugging in for RA, we have UA T minus T cool is equal to delta HR volume times K Ca naught 1 minus X. Of course, both of these are squared because it's second order. And now we just solve for A. From here, A is going to be equal to delta HR V K C A naught squared. 1 minus x squared divided by u times t minus t. Cool. Now, assuming that the reactor operates adiabatically, we need to know what temperature TR does the reactor reach for XA is equal to 0.9, and we're given the heat capacity of a CPA. So, from class 12, the slides in class 12, you're given an expression for an adiabatic reactor, and under the assumptions that CP is constant and delta CP is 0, you have the expression TR is going to be equal to T plus negative delta HRXA over the sum of theta I CP I. Now in this case, the sum of theta I CP I, it's pure A entering. Let me make sure that's correct. Yeah, feed is pure A. So, scrolling all the way down, this is just equal to CPA. So we have TR is equal to T plus negative HRXA over CPA. And if we plug everything in, we get TR is equal to T minus 0.9 delta HR divided by CPA. Okay, multiple choice. Under adiabatic operation, with the feed having an initial temperature of T, will the time required to reach 90% increase, decrease, or stay the same? So, in this case, in this case, it's exothermic, so heat is being produced. That's stated in the problem. So, if it is adiabatic, K will increase as the reaction occurs. And from our original equation, we know that T is proportional to inverse of K. So as K increases, T will decrease. So the answer is B. All right, on to problem 2, maximizing selectivity. So this is a multiple choice problem. So in this case, we have two reactions. We have a favorable reaction where we're producing our desired product D with this rate law, and we have an unfavorable reaction producing an unfavorable product with this rate law. Now we need to decide which set of reactors is ideal. One where we dump in all of A and all of B, and then it goes through a series of reactors, or we dump in all of A, and then we gradually add B into a series of CSTRs. To do this, let's talk a little bit about the behavior of these reactions. So to do this, we want to find conditions. So we're going to find the condition where the rate of D is bigger than the rate of U. So if we look at these rate laws. First of all, it's important to note that the concentration of A doesn't change. We assume it stays constant through all of these, but that's kind of less important because the thing that changes, I guess I should say, is that whether B is introduced all at once or different. Now, if we look at these two rate laws, under desirable conditions, the rate of D, will be higher when the concentration of B is lower compared to the undesirable rate, where the rate of U will be higher if the concentration of B is higher. So, because of that, we are looking for a system where the concentration of B remains lower because if the concentration of B is lower, R of D is more favorable than R of U. Based on that information, we know that option 2 will give us more desirable product. On to the last problem. This is another multiple steady state problem. So the following data was given or was taken using a jacketed CSTR. We're given R of T and G of T values in a table. So it asks us to write all reactor temperatures in which there is a steady state. Of course, like we talked about last time, we are looking for where R of T is equal to G of T. That happens twice, here and here. So we have 2 steady states. In one, we have T is equal to 400 Kelvin, and 2 is T is equal to 410 Kelvin. We have to categorize them as stable and unstable. Just like last time, a couple problems ago from the 2018. It's stable if at T is higher than T of reaction, R of T is greater than G of T, and unstable if G of T is greater than R of T. So looking at the 400, we're going to look at this 405 point. So at 405, we notice that R of T is less than G of T. So because of that, this is unstable. Now looking at 415, we see that R of T is greater than G of T. So this is stable. Now, for part C, it asks, over the interval of the data provided, assuming that delta H of R is -50, what is the maximum conversion? Now, maximum conversion occurs when G of T is maximized. So we're looking for where G of T dt is equal to 0. If you kind of look at G of T, if I were to plot it really quick, so this is temperature, G of T, can you kind of see how it's increasing, and then coming down if this is like 395, 400, 405, 410, 415, right? So we want 410 for our point. Now from the class 13 slides, we define G of T as negative delta HR X. And at this point, we're able to find X by looking at the heat generated compared to the heat of reaction. If every mole that was being generated was being converted, so X would be, or wait, scratch that. We're just rearranging this, although you get the same thing. So if I rearrange this, I get X is equal to G of T over negative delta HR, which is equal to 40,000 joules per mole divided by a negative 50,000 joules per mole. Watch your units. This gives you an X of 0.8. That's the end of this problem. As you can see, it shouldn't be terribly complicated. Before I close this out, I do want to talk about one more thing. Before I say anything, no, I have not seen the exam. Last time I talked to Dr. Nigra, it hadn't been written yet, so I can't know for sure. But over the last 2 years, there has not yet been a question on ignition extinction curves. So I would guess that there is a chance that an ignition extinction curve will be on this exam. So I wanted to quickly talk about ignition extinction curves. What an ignition extinction curve is, if you haven't seen them before, they look like this picture that I just scrolled to. what this is, it is describing multiple reactor conditions. Now, points on the solid lines are steady, stable reaction conditions. These dotted points are unsteady reactor conditions. And then this bottom is your entering temperature, so your T naught. This is your reactor temperature. And this is just kind of essentially a way to describe it. So this is another way of saying that if you had a conversion temperature and you had like this curve, you can have this one, this one, this one, where like all of your energy balances change. Mass balances, energy balances. Anyway, this is essentially just describing every single point where this crosses, where there's an intersection between any of the lines. Can you kind of visualize that with me? Hopefully that didn't confuse you too much. Essentially, this is just a way of describing reactor conditions. Now, the reason that this is important is if you notice, there's two branches. We have our lower branch and our upper branch. This line right here, this point is called an ignition point. And we call it that because we are igniting from our lower conversion conditions to upper conversion conditions. And this is an extinction curve. Or this one right here is your extinction point. Extinction. Sorry, spelling is hard. Because we are extincting the reaction back down to the lower branch. The most important thing to understand about this curve is if I am at 0.4, but I would like to be at, so I'm at 0.4, which means I have a set inlet condition and I'm getting low conversion. But I want this set inlet condition to give me high conversion. I want to be at 0.6, so I want to go from 4 to 6. I can't just magically make it happen. What you have to do is the only way to get up there is you have to move up your lower branch to your ignition point, where it will then ignite up to the upper curve. And then you have to ease it back down. So, to get from 4 to 6, you have to increase TO to 10, essentially. Then you will increase TO a little more, so that you are firmly up on this upper branch, and then you decrease TO until you reach 0.6. Similarly, if you were, and I don't know why you would be here, but if you were, actually, pretend you were under a situation where your inlet temperature was changing, and you were at 0.9, and your inlet conditions started to decrease in temperature, and you got below this point right here, your conversion in your reactor would drop to the point on your lower curve. And if you wanted to reinstate your previous reactor conditions, you would again have to heat all the way up to this point before you backed temperature back down to reach 0.9. So these are incredibly important if you are ever fiddling around with reactor conditions and things change. That's when these are really important. There's also a problem on homework 7 where you create one of these and then you have to interpret it. So understanding that if you want to switch branches from upper to lower, you have to go past the boundaries of those branches and then ease back in, and that's how you will change from lower to upper. Hopefully that clears that up for you. I personally wouldn't be surprised if this ended up on the exam because it hasn't been tested in the last 2 years on this particular midterm. Well, hopefully this was helpful for you all. Hopefully it cleared some things up and helps you study for your midterm. I hopefully will see all of you guys in office hours. Well, see you through my computer in office hours on Tuesday. If I don't, good luck on your midterm on Wednesday, and good luck with the transition to online courses. If you guys need any help or any support beyond this class, and you need someone, feel free to talk to me, and I'll do whatever I can to help you guys with the transition, because I recognize that this is really hard. So good luck and have a good rest of your day.